since like a lot of you loved the session last time, we are having this follow-up session. Hope this session is useful and valuable as well. Over to you, Rishabh.
Yeah, thanks, Dichita. So last week when we were discussing about the Lakehouse architecture, we sort of concluded on this particular part, which is that generally a client sits on when you start querying, a client sort of sends a query, then Delta Engine and the Spark SQL do their part, like they get the information from the meta store that where the data is located and how it is partitioned and all. And based on that, it sort of prepare a query plan. Then they divide those tasks to their Spark core, that the parallel processing engine. And that has like two components. One is the driver query, and then there are workers. So workers sort of pick up certain tasks, and then driver sort of works as a communicator across those tasks, and all shuffling happens. This is another part that when Spark sort of prepare the query plan and sort of prepare the parallel processing, it looks for the resource manager to negotiate with the resources that how much of them are available. And then they sort of hit the storage. They run the read queries on the storage part. So last session we concluded on this one. Today I'm going to deep dive on the specific parts. One is the storage, then how storage is helping out bringing the performance, and second is like the query engine part, that how the query engine is sort of working behind the scenes and what are the things that a query engine needs to take care in order to bring a good performance. In the last session, there were a couple of calls on the Parquet versus like CSV as well. That how that is going to change the equation. That is there a performance gain when it comes to Parquet. So we'll learn all those things in this particular session. Um, We'll start in the storage part. First, you need to understand that the like when we are designing whether the storage or whether the query engine, one must understand there are certain differences in the transactional, the relational database world versus the analytical or the big data workload. In terms of purpose, when you have a transactional database, which you generally use for the live application, you have tight SLAs, and it's generally the customers who are interacting with those particular databases. And then this is required that whatever you are committing, that gets no, that gets stored in a non-volatile format, and all atomic related, consistency related, acid properties, whatever are there, are meant in there. So generally in the transactional world, these are the requirements, while in the analytical world, the SLAs are not tight. Generally, the queries can perform even in seconds, even in minutes as well. People are okay. However, a very heavy queries which can run for a very longer period of time, that can also be the case. But like the big data today, the Spark has optimized it for bringing the performance up to something like a minutes phase or a seconds phase. If the data is too heavy, then definitely it is still going to take a lot of, it can take hours to dig in. Like if you are sort of querying the entire data, trying to run a query which is a year long or a for the entire historical data you are trying to sort of chime in one go, then things may take time. But in general scenarios, the transactionals are something like milliseconds, like probably 5 milliseconds will be the query time, and few more seconds will to do in order to like when the data will move from the SQL server to your application server. In the analytical world, generally the analysis does take a longer period of time, because you are dealing with a lot of data, not just a smaller chunk of data, but your users are limited. They are generally the BI ops or your internal teams are the users of the analytical world. Even if you have to expose your analytical thing to your end users, like our publisher or advertiser, the general way of solving it is that you behind the scene do the analytical work, then you push it into a transactional DB. If the load is very high, if you have like if the requirement is that you have to show the analysis itself on your front end to your end users, then probably that is the hybrid approach that is sort of being taken today in the world. And that's how, like, that perfectly works good for the people. And acid is something which is good to have thing. It is but still, like with the delta lake, things are like acid is also sort of in force. But before that, when these were not in force, when Spark used to process, uh, so not the Spark, but if you look at the Presto, it does not do any type of fault tolerance. But given that it was doing just the read part, or even in the ETL part, they were like the HDFS file writer. There were one version which were using the ACID one, but was very slow in nature. There was another one which was not, which was fast but was not following the ACID transactions law. So that's how the like the map reduce word used to look like, or is it look like even today. Now the delta has bring sort of a lot of values in there, but before like diving into relational versus non-relational versus big data, one must understand that things are quite different in the two world. Now, when I have talked about the transactional versus analytical, you must understand that generally the transactional databases go with an row-based approach, because you generally fetch one particular item, one particular user details, or one particular product. Think of like a Flipkart website. You need to search, then you go for a particular product. Most of the time, you will be listing few rows at a time, and that's how you will be dealing with the data. That's how the type of interaction you generally have. In the row based approach, we'll talk about the second part where there is an advantage, while in the columnar one, which is mainly used in the analytical world, uh, which is good for doing the roll up against specific columns when you need to prune the columns quickly, rather than like the requirements in analytics word is generally like you pick up 2-3 dimensions, two three particular columns, like you need to get the total one against a country ID for the particular time period. So generally in the columnar databases, there are specific 2 or 3 keys based on which you sort of partition your data. Rest all are sort of stored in a columnar fashion, so that when you sort of want to work with a specific column, you can quickly jump on the specific columns only and sort of do the roll up quickly. So you do not. So specific, what is the big advantage? Like how should one go with a row versus columnar? The thing is, in like why this matters, that whether the data is in the row format versus columnar format. In Excel, if you will look at, it gives you both sort of a view. You want to work with a column, you sort of select all the columns in a row. You can select the entire row as well, but behind the scene it's a disk, that how it is storing, and how you can quickly pull the specific data is what matters. It is quite expensive in terms of performance mainly. Like reading it from a disk is not as performant as reading it from memory, or uh, like the IO is far more expensive than the memory ones. Okay. Now, why the row versus columnar? If you look at the two queries, I'll showing you two different. Like suppose the data set is a small one, but you need to think in a larger one picture as well. But let's look at that. This is the sample data that you have, where there is ID, name, department, and pay. And if you need to select one particular item, if you're in the row versus in the transactional world, you will probably will be interested in at a time in the pay of a particular employee or something like that. What is the department or something? In the Colmer, in the analytical world, your queries are mostly equipped with the group by statement, and generally your data you need to query, you filter first by the time window, that in this particular time window what happened, and then you sort of try to get the data. Now think of this, the two scenarios. The second scenario, that select department comma sum comma pay from a table group by department, that if the data is in the row based format, and suppose I sort of save the information of the each row, that this particular in the disk block, this particular item lies in this particular block, this particular item lies in this block, and this particular item lies in this block. Okay, because generally the disk is generally nothing but the blocks of small pieces. Now if you will store the data in a raw format, getting a group by statement means you will need, if this is lying in three different blocks, which means that you will need to read in all the three blocks. Okay. While if the data is in the columnar format, which means that you will be reading probably only the two blocks rather than reading the three blocks, the only the one which are in the column. So you have stored in the columnar fashion. You have maintained that order based on which you are able to sort of index them, that this is the order and this is how you are going to sort of query the data. So this is the main reason that when row versus columnar data becomes important. The CSV file or any file in general, when it is getting stored, they are stored in a like when it comes to CSV, it's a bytes, so you can never read it, never skip it. Whenever you will need to go through the CSV, you need to open the entire file and you cannot actually skip any part. It's like that. CSV does not store that the new line is in the second block or in the third block of the disk. So that part is not possible in the CSV. But when it comes to Avro or other row-based approaches, then there is a possibility that you can skip the rows. In we'll talk about the transactional word also, that how the row-based approach, like how the indexing happens in the relational database. And then we'll talk about here that how in big data things are little different than what we see in the relational world. But this gives you a sort of picture, like in a layman's terms, that the columnar databases becomes important when you have a lot of, like if there are hundreds of columns, then the data lying in a raw form in the row based format is going to turn into a larger IO operation as compared to the columnar ones, because the columnar ones will let you skip lot of the column, lot of the data. Like if the data is stored in this particular format, then you does not need to read the first two at all, because this part is actually stored in that header of that particular file. So CSV does not contain any sort of a header information, but Abro or any other formats like Parquet, ORC, they do store the certain metadata information, that how their data is arranged, and thus they are able to achieve a certain level of performance while reading the data. So mainly it's about mainly skip reading whenever it is not required is what is the principle to sort of gain the performance in any of the word. So now when so Parquet is one of the format. I'll talk about Parquet. This one slide which is upcoming, which is more about the relational database versus the analytical one. Okay, but before that, I'll deep dive into this one of the format, which is Parquet. So how the Parquet format actually is in the metadata information, or generally the files, whatever data you have, if you have 1 million records, first those 1 million records will be divided into chunks, probably a 10K chunks. Generally it is based on the size of the file, which is generally 128 MB. But if it is not, but in a layman's term, you can think of like if there are 1 million records, it will sort of divide, it will keep 10 it will keep 10K into 100 records in the file system, and it will store each 100K chunks, each 10K chunk into a columnar format. We'll talk about that. And then there is a compression also. Compression brings another value. So think like if the compressed value is there on IO, when you will try to fetch the data, you need to decompress it. So you need to make sure you need to understand that decompression plus IO is cheaper than the reading of the entire IO. So if you are reading the uncompressed value from the system versus you are reading from the compressed version and then you are decompressing, the total time in the decompression in memory is lesser than reading it from the from the uncompressed version. So if the things would be other way around, then the compression would not have played any role in actually bringing the performance. So though compression, there is a secondary advantage that compression is bringing you a lesser cost in the storage, but that is a secondary advantage. First advantage, which is the engineering advantage, is that it is reducing your file reading time actually. So yeah, in the file system, the same way the above three things, just a graphical representation that the file system, you will have this part file 1, part file 2, part file 3, part file 4. In each part file, there will be each columns will be like the information about each column will be stored in this particular fashion. That the column 1's data is residing at one place, column 2 data, column 3, column 4. Whenever if you are looking for a country ID and a total one, or column 1 and column 3, it will just read column 1 and column 3 because the metadata information that lying on top of it will tell you that you need to skip the bytes from this place to this place, which will skip a lot of IO reading. Then the same thing that for each columns, there are informations like min max as well, which can let someone skip the entire file itself. I'll come to that part as well. So there is another, which is the compression, dictionary compression, which is a minimal view of the snappy compression that Parquet that on top of Parquet one can apply. And this is how it looks like. So in the uncompressed data, the data was written in that United States, France, Germany, Netherlands, France, United States. The dictionary compression sort of did that, assigns the values on it, and then the encoded data was looking something like this: the 0, 1, 2, 3, 3, 3. There is a further run length encoding that whatever things are looking close to each other. So the 3 was appeared at 3 times. So it put it as a 3, and 1, 0. So this is one example of compression. And when somebody is reading that, how quickly it can read certain part of the data. Now, one thing that one needs to understand that the dictionary compression is not something that we always should apply. It always depends on that how many distinct values lies in the system. If there are too many distinct values, if this is a string that is put by every individual row that is not sort of it's just one or two, then it will not bring that much of value. But in most of the cases, the values are very repeatable in nature, and thus the compression sort of uh, brings the value while fetching the data from the disk itself. Now, after fetching the data from the disk, it's required that one has to again stitch that back, that uncompressed value. So that part, because the data nature, the randomnesses are of certain nature, the decompression time is always uh, lesser than reading the compressed data, reading the uncompressed data. Cool. Anyone, any question so far? Okay, I'll move to the next portion. Like we have talked about the Parquet format then, but we were talking about the Delta format, that Databricks Parquet format was there earlier as well. But what is the Delta format that is there? So Delta format was not nothing, but they were using the same Parquet files only. The only advantage that they sort of put there was they sort of provided a dedicated metadata storage. So when you saw this, the information is lying in the part file itself, that what is the min max values, based on which that you will decide whether you need to skip that file. Now, file opening itself is a big operation, is a big performance headache. Now, if the metadata information about each individual columns is lying at one place, then in one single file opening, you can skip the opening of multiple part files itself. So the delta actually bring one value there. It's first value that it brought by putting a dedicated meta store. So if you see, you can see in the right hand side in the delta log folder also it creates along with the same Parquet file directories. It is same as what Parquet, when you will use a Parquet writer, it is going to be same. In the case of Delta, it will sort of pull that information while writing the data. It will also sort of put that metadata information into different JSON files. And generally it's also follow the same rule, like if this is becomes like around 128 MB or large enough, then it sort of uses the second JSON file. And then there is a checkpoint information which sort of tells that which files are active in the system, which is more related to whenever there is an update operation under the hood, it actually creates another file in the system. So if the file one is getting updated, it will sort of generate file one prime.parquet and will mark, and in the JSON file it will mention that the only the active ones is the file1.parquet, file1 prime.parquet, and not the file1.parquet. Now the file1.parquet, it the data which is redundant in nature and is not sort of applicable all the time, but may be useful when somebody wants to roll back a particular thing. Uh, that data resides in the system, and there is a concept of vacuum. It automatically triggers, like if there is a default timeout is like 7 or 14 days, by after which it sort of removes that file. Otherwise, you can put that you can configure that time while putting the data into the system. That way also it can work. Okay, but it can help that time travel feature of the Snowflake, or like time travel feature which we always talk about, that if I want to revert to a previous version, then there it helps in that sense. So the file, if the file one was of 1 GB, but it got rewritten for just one particular record, then it will be consuming 2 GB of data actually. Eventually it will be emptied, but still it will sort of helping you maintaining the different versions. So that is the another value that delta format sort of brought in. So the acid rules are sort of maintained by that particular thing only, that they never overwrite the file in actual. They sort of recreate a new file and then put it. So in the term at the time at the time of like, it will not impact a read or write performance, but it will definitely take your storage at certain amount. The write performance will be impacted for writing delta logs for a little bit, but not that much. Uh, but on the other hand, this helps in skipping the files faster. It helps you bring the acid rules to the lake itself. Now there is a third thing, which is G ordering, which that information also sort of reside in the delta log. So what G ordering actually means is that once you have partitioned your data, you have, so here you can see that the date is 2019-01-01, file one dot parquet. Let me go back and just show you the Databricks portal as well. So we take the fact. Use a Snowflake one. Right then. I to open any fact, you can see this is called the partitioning or the. So in Snowflake, there is only a concept of partitioning. There is no concept of geordering. I'll tell you like what is the. So if your frequent queries are on certain columns, so generally you always choose date as your column while you are querying the data. Generally you want to query in a particular window. And second part is like if you are thinking about that, what if there are not date tables, which generally are the metadata type of information. For them, you do not need to partition the data generally. You generally keep it in a one place. It's like 59.2 MB. This is a small dimension tables earlier I was talking about. And generally, you unless they are very big in size, like if they have crossed 10 millions of records or something like that, then only you will sort of try to put a partition on them. They are thought of as a small tables, and generally drivers what they do is up to certain level, if the file size is very small, when it tries to distribute the work, it sort of creates a copy and distribute to every node for that particular part. While for the big data, it always assigns that you pick the certain partitions. So if you see in any in the so here the data, whatever are the different values for these particular things, they will be created as folders in the system. So process time equal to A, request time equal to B, event time equal to C. So there will be the folder structure till the end, and after that there will be files. And whenever your queries are running, they will sort of there will be one is the partition pruning, that they will do the whatever time window you have chosen. It will prune that it has to read the data only from these many files. Then second, all the other filters that are there, for that it will try to do a file skipping, the part file skipping. So in the part file skipping also, it is necessary that you do a geordering on certain columns only. Not if you will try to do a geordering on all columns, it will not actually work, because essentially geordering is also like the first column will be sorted fashion, the second column will be like a comma B fashion. So that will actually not be sorted, but it's still some sort of thing that you will be able to achieve. Now think, suppose if you put the process time and event time or the time one to be your partitioning key, and if you do the G ordering on a particular thing, then it'll come to next slide probably. One second. Okay. Probably in the query engineering part, I will sort of explain that how geordering information will also help skipping the files. But this is the main storage sort of region, that why people choose from the raw, like why the raw format is being used in the traditional or the transactional world. And the actually the next query engine part will sort of explain it in a complete sense. And the second part also, that why the analytical word is using the Colmar one. So probably the next section also will sort of give you a full coverage that why row versus columnar are important, both from the storage perspective, not from the, it's more mainly about that why there are decision change between the two world, that one uses the row based approach, another uses a column based approach. So far so good. Any question, anyone? Okay. Yeah. We'll move to the. Sorry.
Hey, Rishabh, just one small question about this Z ordering part. Let's say we configure one Z order now and there is a previous data already available. To apply this Z ordering for previous data, do we require to do some processing or it's automatically taken care by the Databricks?
It will not be automatically, so it depends. So if you have put the auto optimize type of thing, then whenever the data is arriving, it will take care of some
Uh,
sort of background processing. Otherwise, it's always for the incremental data. It's not for the, so tomorrow agar if you decide that there is a different column for which geoordering should be applied, just found that there is another column which is more prominent for the query for the reading purpose, then for the previous one you need to reshuffle your data again. It will not happen automatically. Yeah.
Yeah, thanks, Hrishabh.
Yeah. Did I? Okay. No. Yeah. So I'll explain this part, the RDBMS versus big data. In the relational database, what generally happens is there is a physical sorting that your data also lies in the partitioned format only in the relational data world as well. But generally the database size is of size 8 KBs. And on top of it, we sort of build a clustered index, which says that where the data is lying, which sort of depicts the physical sorting only, which is a B plus T type of a structure. There is a, and generally not all databases sort of expose this word called clustered. Generally in SQL Server, you will see the word clustered index and the non-clustered index. And clustered index is unique because you can only sort the physical data in just one single order. While whenever you create another sort of indexes on the on any other column, they are non-clustered index, but generally they also sort of point the data in a certain fashion. Either they have pointers to the clustered index, they have also pointers to the data page also they might be having, but generally they sort of takes help from the clustered index to find the data in a quicker fashion. So if it is a logarithmic time that clustered index take, it will be 2 times of the logarithmic index that the non-cluster takes. But generally the processing is so fast that it's not really visible. And whatever is the network part and the processing part is there, that supersedes does not let you even know that the clustered indexes are generally faster than the non-clustered one. While in the big data solution, we do not prepare any indexes. It's mostly because the data is lying in so much pages, like they are lying in the in like a big files. The file size is generally higher because your data is also in TVs, not even in GBs. There are like it. So to process the TV, to dig down the TVs of data, you need to essentially make sure that you quickly escape the non-essential part of the data which you don't need to read. So here the power of the performance is arrived is sort of comes from the partitioning or bucketing. Bucketing is same like partitioning, which is like if you want to, rather than if the data in one partition is not good enough, suppose your data you always so do on a country ID basis or something like that, then doing a bucketing might be better because too many small files will not bring that, may degrade the performance. So you can do a bucketing. Generally what InMobi has, like the data that we have in InMobi, there is a good amount of data in each partition itself, so each partition can work. But if the data in different partitions are like very small, 10 kb 10 kb, then probably bucketing might help, that you sort of say that the data from 1st April to 10th April is lying in one bucket, from 11th to 30th is lying in another bucket or another folder. So that is also possible. So in big data, the partitioning bucketing is a big part. Then the stats that are available there, they help sort of prune the number of files that one has to read, and then the power parallel processing that different workers will pick up the different data sets. That's where that splitting of files actually helps, that if there are multiple file records that are there, those will be helpful to sort of give the jobs to different workers, and thus they are able to bring that much of performance. Generally in big data also you are seeing like if the queries are of nature that is of like you just want to query like give me country ID and total one for the period of X comma Y. If the date range is pretty small, then within 400 500 milliseconds you will get the data also in that case also. While in the relational database is like 5-10 milliseconds for the most of the transactions. Definitely things might change if you will have a different type of query and all other things, but generally the typical use cases like the relational databases perform at like like a single digit milliseconds. Big data solutions, they can go up to, as of today, the Spark, we have seen like 1 minute is something, the 5 millisecond, 5 second is something which is a like a P95, and there are many queries which runs more than that particular time also 1 minute. And definitely then if there is a nature of query that changes, it can take even hour or something. That is also possible, but generally that's not the case for most of the queries. So yeah, so same thing. There is no separate index concept. These three concepts sort of drives the performance in the big data solutions. And you need to understand also that there is no need of having that B plus T like index as of today. Tomorrow, if the partitions itself becomes like a big problem, if you are having data in so many partitions, then probably a one new thing that might come in, that the partitions itself might be getting indexed at some place. But that is a separate part of the problem. That's still not putting the indexes to the data itself, the data that is lying in one TVs, that nobody is sort of indexing. Another thing that I also need to understand is that when the data is that is lying in the analytical world, you can query on any cut. If you are putting like a country ID, OS ID, or 100 different columns, they are there, and there are measures like total one, total clicks, total install. Things can People can query on any cuts, and that's how people wants to use the big data. It should not be a restriction that only few ones should be faster and few ones should be slower. So while partitioning is bringing one value, and G-ordering is also sort of can give you certain performance benefit, but there is a particular requirement, which is you can query across any cut. While if you go in a relational database and if you do a non-query, non-index column, and if the data is in like a trillions or something, the query will be stuck. And there are chances like if there are other queries which are also running, there are deadlock situations might be happening there, and you might need to restart the server, or you need to send a kill signal to the query. So the relational database and big data, the type of workload, it is different. Things are little different. There are performance like the performance driver. There are different performance driver in the two word. So you can say this is an index also. The partitioning plus geoordering mixed can work as a index as well, or partitioning and stats can work as an index. Stats, there's also one more thing that which people should not confuse. In relational worlds also there are stats that relational databases keep if you don't turn off them, but those stats are generally used to determine which index to be used. If there are multiple indexes which can be used for a particular query, then stats are used to know that where the density will be different, like based on the density of the data, it will try to use that particular index so that it has to travel less within the index itself. So that is also there. But this stats is say in same nature, but it's quite minimal in nature in big data world. And with the parallel processing, we are able to achieve good amount of performance. And yeah, we need to do a more of the group by here, while and the filtering is on a very little less number of columns. The filtering is generally like one is the partitioning column, the date column, and there may be some specific API which is relevant for the end user use case. Those are the ones which are popular in big data, while in the relational database you always have that you will be querying on these particular sets. Like the filtering conditions are more diverse in nature, and group by conditions are very minimal in nature, while in big data the group by is more prominent. And when you are dealing with group by, you need to find that all the data that you need to group by is residing as close to each other. You can pull it in a very quicker fashion, do it the compute part, and then give the result to the end user. Now we'll talk about the query engine, parallel processing part, and the MapReduce versus Spark. I have added the slide, but I will skip in interest of time. It's already I guess 450. Yeah, 445 is already there, so I'll sort of put it in a quick. Like I'll skip the MapReduce versus Spark. I'll talk only about the Spark only. Will not talk about the difference. I have added the slides. If you want to go through, please go through that also. So generally, how so map, so whether it's Spark or whether it's the map HDFS map reduce, though the name is not there in the Spark, but it's essentially do two tasks. One is the mapping and the reducing. So suppose this is a big file. Think of it as, suppose this particular text is there, deer, beer, river, car, river, deer, car, beer. So generally, when you will put the data, you will sort of divide it into certain fashion. So suppose you divide into three particular file. This is called partition. In real use case, the date is the key based on which you divide the all your data or timestamp. Then what will happen is you need to do the word count. This is a word count program. So the one partition, each worker will sort of pick and will try to calculate, try to map certain things that it will divide, it will do the split and will try to assign a number to each of the words. Then after that, it will do a shuffling that wherever deer is present, try to shuffle it across different workers. Two workers can also pick up. So there are job slots would be there in different workers, and driver sort of push that task to those workers. And then this is the reducing part where you get the data, you couple it that these are the number of counts that are there, and this is how you sort of get the final output. So this is the entire processing that happens whenever uh, you do a data process or the query in database or in the big data world. So this part is taken care, that splitting of the part, the partitioning is taken care at the time of the writing. The second part is general is something which is taken care at the later point of time when you are querying the data. Okay. Now, earlier also on the Parquet files, I was telling the same, I was representing this thing. So you can think that suppose there is one big files which was divided into two partition and there are three columns, which is bucket owner, fruit and count. You did the pre-processing and you sort of derived these stats, and these are the stats which are lying in your column format. Then Parquet will be storing something like this for the bucket owner, that the min value in this part file is Ashish, max value is Vishal. For fruit, min value is apple, max value is grapes, and count, the min value is 10, max value is 50. Similarly, for the part file 2, it will sort of have the same information. Now, suppose there is a query which says you get me the data where the fruit is banana and you need to sort of find that bucket owner and the sum, like it's mainly that how many bucket, like how many banana owners are there and how many bananas they are holding. This is the query that you have to do. Then the first part is that you need to prune the data where fruit is equal to banana. Now if you will see the min max value, the part file 1 will have the chances of banana in it, while the part file 2 will definitely reject that banana is not here. So the part file 2 will not be read at all. Uh, in the Parquet world, the file opening will be there and then it will sort of close the file handler. In the Delta world, it will not even open the file. It will just read the part file 1. Okay. Think of another scenario where you are saying that the fruit is and the like for the Gavru, how many, like give me the fruit versus count mapping, that how many like how Gavru is holding which all fruits and what all amount. Then you will see that both the files will be read because the filter condition owner equal to Gavru, the Ashish Vishal and Abhiram, the G can lie in between both of these. So it will result in reading all the, in opening both the files and reading data from both the files as well. Okay, but yeah, but in this, okay, we'll go back. Okay, so it will end up reading file data from both the files, not just from the one file. Okay, so this is G-ordering, where G-ordering works like wherever if your filtering conditions you know upfront that your query runs on these particular columns. Apart from, they should not be the partitions one. Other than the partitions, actually they should be. And then it will sort of sort them out. Then there are chances that the data in the fruit if you have done the geordering on a particular column, suppose if you have done it on a fruit column, then then this particular file will be having the sorted values for all the fruits, and similarly this one. So at the time of query, you will be quickly be able to skip the part files or the file reading part. Okay. Now think of another scenario where you are looking for that give me the count hold by each individual owner. Okay, now this definitely is something which is you are saying that you need to read data from both the files. You need to know the count, you need to do the sum, but the columnar format will give you an advantage that you will skip the reading the fruit column at altogether. You will just read the two columns, which is the bucket owner column and the count column. So if there are if the number of records are not increasing, but if the number of columns are increasing, then the performances will not be impacted in the big data world. So this is how the Colmar sort of brings the value into the picture. Okay. Now this is the entire like the how the query part is like the how the parallel is also sort of part of the mix part, like how the Parquet is sort of bringing value or the Colmar format is bringing value, and how the parallel processing is bringing value to the big data world. Now this is all about the querying. There is another which is a prominent question because there are Spark, there is Presto, there is Databricks. What is the difference between the all three things? This is a lot of times we sort of when we sort of introduced to the big data world, at the same time we got introduced to multiple technologies, which is Spark, Presto, Databricks. So just to give you, this is just a difference that Databricks is a company which is started by who sort of developed. So there was a group in particular university who developed this open source Spark solution. Those same people sort of opened the company called Databricks, and today they sort of offers you Spark in two different in like multiple products which are based on Spark, which is one is the SQL endpoint, another is their Spark cluster management itself, and ML flow also sort of is sort of integrated with Spark. So Databricks is a company. Databricks is one can say whenever because all of these are like what is common in all is the MPP part is common in everywhere, that all of these are massive parallel processing engines. Okay, now there are certain part which certain things do, certain things does not do, because Databricks has developed a SQL in like more of a SQL interface on top of the Spark core. Spark core is the massively parallel processing engine. Spark SQL is something which will help like which file to skip, which file does not need to skip. So it's more of a it's sort of do a work which is a pre-job like pre-computation for job orchestration part, while that how those job will be orchestrated for the data processing. Again, the job orchestration is just for the data processing part, not for it's not a general job orchestration engine like Airflow or something. It's just that for the data processing part. Presto is also a parallel processing engine. Okay. However, Presto was not developed for writing the ETL jobs. Means the transformation of data and writing the data is not what Presto was developed for. Presto was developed only with the intent of concurrently doing a massive number of queries on the same data. So it was developed mainly for the reading part, while Spark was mainly developed for the ETL part. Uh, and and that's the reason that if you will for the same set of Presto, if the delta is not there in picture, then Presto will work a little faster than Spark SQL. The reason being that Spark sort of has that recovery mechanism, bookkeeping it does for whatever data it is processing, while Presto does not. If the Presto query fails in between for whatever reason, maybe network failure, whatever, maybe some other reason, that query will fail. It will not try to recover. Spark, however, will try to recover it. And because since it try to recover things, it has to do a additional bookkeeping, because which it might be it is little slower than Presto. But nonetheless, the Delta engine, the Delta format is bringing value to the Spark as well. The Presto is also getting integrated with, like, this is not an open source Presto which is getting integrated with the Databricks. delta format, that it is not taking advantage of the information that is lying in the delta log. But the enterprise edition, which is the Starburst company, which has done the same thing the Databricks has done to the Spark. Starburst is the company for the Presto, managed Presto. They are leveraging the delta format for doing this for the like bringing that to the Presto as well. So I hope I am clear, like people are clear about Spark, Presto, and Databricks. Okay. So yeah, I'll not go on to the fifth and sixth section. Uh, I have already talked about the optimization, that how the different optimizations are there. The Databricks, there are like where it is a like if you can read about different optimization that I've mentioned here. The optimal file size. Arco in his first session also talked about the data pipeline optimization. He talked about this target file size, that when you're dumping the data, the part file should be of the specific size. If they are too small, that means there will be too many files that might be existing in the system, and you may result in too many file opening, and that may be a lot of job orchestration job as well. The job orchestrators have to take care of the large amount of jobs. So it's a booting time, just like a booting time, it will increase if there are too many files. In the if there are too large files, if there is a too big files, then it means that you need to read the entire file. You need to the cuts that you were seeing in the G ordering with the min max, that will not be possible. So generally for 1 GB, generally you take like 10 MB or 100 MBs of files in different part files. So that is one optimization that you that is sort of helps the query engine to do a job. It's in a more optimal way. Cluster one is also something that already Arco was describing, but it's the different, that is a Spark cluster based. Then the compression also I talked about, that the decompression is cheaper than IO. The decompression and pulling the IO, the decompressed value. So generally when you sort of compress the value, uh, at least 40 to 60% of compression you generally get on a data. There may be someone may generate a all type all different type of data, which mean result in a very less number of compression or a very large compression. Think of that, if the data is just once in the file, just one for the 1 million times, then that can be compressed in like a 1 into 1 million I will put in, it will become a 1 KB data. Doesn't matter how many bytes might have object in an uncompressed format, but in general the typical data you are able to achieve a good amount of compression. Almost the file size reduces by 40% to 60%. And to decompress that data whenever you need it, and you only decompress that particular data that is of your interest. The metadata information about each individual column is still uncompressed. So when you will be reading that meta files, meta information first about all the columns in one go, you will be able to realize where the entire information about that particular column lies in, and you will only decompress that particular part, and that's how it will save you a lot of IO there as well. Then about the indexing part I told is same, like the partitioning, bucketing, G-order, and this is dynamic partition pruning, which you can also read about, which is mostly applicable when you want to cast the date into uh, month or something. So there are information which lies within the date struct itself. Then how the DPP is something try to leverage that particular part. In the SQL part, there are cache, small table, autoloader, which also Databricks provides. So cache is one thing, or like different data sets it can cache. Another part was that all small tables, like if the table size is less than 10 MB or 15 MB, whichever you configure, then those small tables generally sort of are distributed or broadcasted to each worker nodes whenever they are in the picture of query. And if you need to do the join, it is not a lot of shuffling that happens for that particular file. So these are the certain optimization that Databricks offers. This is yeah. Now, so far, any question, or can I take more time, Dichita, or should I close?
No, Rishabh, it's okay. I think you can continue.
Okay. So Snowflake to Databricks, because Snowflake was the data warehouse which we earlier was using. The Databricks is where we are moving. The Databricks is something where wherever the data lies, you can directly query on top of it. While in the Snowflake, you need to ingest your data into the Snowflake system. But the advantage is when you are ingesting the data into the Snowflake system, the optimization or all the partitioning related thing, it's a one click. If you tomorrow wants to change a clustering key or the partitioning key, that then Snowflake will automatically take care. It's a one click thing for you. But while in the Databricks world, it's something which will come to the developer itself. Queries are fast in the Snowflake world, both in the Databricks POCs are showing that queries are running faster here as well. So here for the queries which used to take time more than 1 second or 5 seconds, they are definitely running faster. For the queries which are running in the milliseconds, we have yet to do that part. We still need to see whether that is also in that place also Databricks is doing a good job or not. Yeah, now there is one developer based advantage which Snowflake gives because it's owning everything. It's giving they work in a multi-tenancy mode. So your VMs are also hosted in the Snowflake world. Snowflake owns the VMs. And whenever they need to spawn, so they already keep a certain buffer of the already spawned virtual machines. So whenever you try to spawn a particular worker or something, uh, especially in the query reading part, because Snowflake is not being used as a for the ETL part, it is just about the big data query part. So whenever you need to spawn a new warehouse, it's quite fast. Within 2-3 seconds, you will get that particular thing. In the Databricks one, if you are hosted in Azure, your VMs will be taken from your Azure subscription, which means that whenever you will need a worker, or whenever you need to spawn a new VM, it will go and sort of provision it and then we'll start using it. So it takes around 5 to 15 minutes of time. If it is a always running scenario, it will look same in both. It's not a big disadvantage, but in a developer, like for a dev environment, it's a little bit of loss for the developer productivity. Not a big loss, it's still a loss for the developer productivity. So these are the major differences in Snowflake and Databricks. If you have any questions, and there is one more feedback that is going to happen, so please stay for 5 more minutes. Otherwise, whatever questions you are having on these, please feel free to ask. Yeah, these are the resources I have mentioned, some of the white papers that you can read upon, and the videos. Yeah, thanks everyone. Any question from anyone?
So Rishabh, I have one question. So on so for reordering, does it work at multiple levels, or can we do just one level of reordering? Because say the min and max and all, if we are honoring for say one column, so it may not be possible to honor for like subsequent columns, right?
Yes, so see, yeah, so generally G-ordering, what is recommended is you do on a 3-4 columns only. It's not like if you, and individually you cannot do it. It will always be a composite in nature. Still, it will be able to achieve some certain level of file skipping because the data is sorted. There are chances, unless it is very much skewed, like if you will do a G-ordering for there is a column called A comma B. For each A, there exist A to Z things for B. Then the G-ordering is not going to bring any help. But there can be certain advantage even there. Like if you are just running on B, because the randomness of the data is so, it can still bring the value at certain point of time. So yeah, so that question theoretically is like theoretical answer is you cannot do individual G ordering. Okay, you have to do a G ordering at a composite way only. Like it is a order by A comma B comma C. It's not like order by A and order by B. That's not possible. And also the G ordering is essentially G-ordering is essentially the file co-location. This is the physical sorting. G-ordering is also a physical sorting only. So just like any clustered index or partitioning, they are always in the one particular order only. You cannot make more than one case of sorting the data into physical disk. The only thing that you can do is you can copy it and then you rearrange it. So that is not the case we currently follow. Does that answer your question, Aditya? Yeah.
Yeah, right. Thank you so much.
Yeah.
Thank you, Rishabh, for again a very insightful session. I hope like this session was of value to all of you, and you had so okay, I can see quite a few reactions, Rishabh. So thank you so much. We hope to have more sessions from you. And thank you everybody for joining in. And please take few time, like 2 minutes to just fill in that poll. It'll help us come back with better sessions. Thank you.